Okay guys, welcome to chapter 5. 5.1 deals with estimating area. So to kind of kick things off here, we're going to look at a classic train example. So suppose we have this train moving at a constant rate of 75 miles per hour, and we're told that this is happening from 7 a.m. to 9 a.m. We want to find the distance traveled during that 2-hour window. Well, you may recall that we have a distance formula. Distance is equal to the rate times the time. So the total distance that we're trying to find here is the rate of 75 miles per hour times the time. Well, the time period is 2 hours. Okay, so the distance traveled would be 150 miles. Okay, so your units here, miles per hour times an hour. The hours cancel, that's why we're left with just miles, right? So our distance is 150 miles. So understand that we could also look at this graphically. So let's suppose we were to graph our rate, which the rate is really a velocity if we were to look at it in terms of its absolute value. Okay, the constant rate is really talking about the constant speed. So if we were to look at the absolute value of velocity, okay, we really are talking about our rate or the speed. So suppose we were to draw our constant rate. So we're talking about velocity and time. Here's 7, here's 9, so that's our time. And we know that the velocity or the rate is 75, so we're going to draw a line going straight across there. Okay, and so we know the answer is 150. Well, graphically, we could actually get that answer by looking at the area of this curve. Okay, isn't it true that if we were to do 75 times that 2, we get 150. In other words, if we were to look at the area of this rectangle, right, it is 2 wide and it is 75 high, so we get 150. Okay, so that leads us to an important discovery. So the distance traveled is going to equal the area, so keyword here, area, underneath our velocity time curve. So in other words, if you were to find the area underneath your velocity function, you're going to have your distance traveled. Okay, you're always going to have time down here. So if we're talking about velocity, the area underneath it is going to give us distance traveled. Well, this is easy to see if we have a nice constant rate of change. All right, so this is a nice straight line, so it's very easy to find our area. It's a simple base times height. We have the exact answer of 150. Well, what if our speed, what if our rate is not constant? What do we do if it's varying? Well, that's our next example here. Okay, so what if the velocity is not constant? So what if we're talking about a velocity time graph again, and you can see the velocity is not a nice straight line going across. So how would we find the area underneath this curve? That's the question we're looking at here. So how do we find this area? Okay, well, later on we'll talk about finding the exact area. All right, and by later on I mean later on in this chapter. But for now we're just looking to approximate it. And the way we're going to approximate it is we are going to make rectangles. So imagine a series of rectangles, all right, with the same width, okay, drawn in here. Now, I'm sure you would agree that the more rectangles we draw, the less wasted area we would have. Okay, some of these rectangles would be above, some are below. So if you were to draw in an infinite number of rectangles, you would ideally have a very accurate approximation for your area. Okay, so what we are going to do is we are going to use rectangles to approximate the area under the curve. All right, let's formalize here a little bit. So when we use rectangles to approximate the area under a curve, we call this the rectangular approximation method, or RAM for short. We also here referred to as a Riemann sum. Remember, the R in Riemann is like the R in rectangle. Okay, So we're going to look at a few different types of Riemann sums. The first one is called the left-hand endpoint technique, or LRAM, okay, L for left. Now, this entails creating your rectangles underneath your curve where the height of the curve is formed by going up on the left-hand side until you hit the function. And then from there you would go over and down to form your rectangle. Okay, so the next one, you're going up on the left-hand side until you hit the curve, and then you go over and down, so you keep doing that. Okay, so that's a left-hand endpoint, or sometimes we call it a left-hand sum. What we would do is we would approximate the area. Suppose we were looking to approximate it between here, and we were told to use 3 rectangles. All right, you're always going to be told, by the way, how many rectangles to use. Okay, so here we have 3 rectangles in our approximation. Sometimes it's known as a subinterval. So you may see a question that says, use a left-hand Riemann sum with 3 subintervals to approximate the area under a curve. Okay, and we'll see some examples shortly where we get into actual values. Okay, then we have a right-hand or right endpoint sum, which we can abbreviate as RRAM. So this is where you say, okay, and suppose again we know we want 3 rectangles, and we're looking to estimate our area between here and here underneath this curve. This is where, for your first rectangle, you're going to go up on the right-hand side until you hit the curve, and then you're going to, from there, work backwards to the left and draw your rectangle. So again, the next one, you're going up on the right-hand side until you hit your curve, and then you're going over to the left, and then making your rectangle. So your rectangles are always going to be the same width, even though it doesn't look like it here in my sketch. All right, the width is always going to be the same. Okay, so one thing to note, that in this first example here, notice how this happens to be an underestimate, because you can see we have all this space inside here. Okay, so this estimate, if we were to find the area of these 3 rectangles, this would be an underestimate. Okay, so this particular case, because we have that underestimate, this is called a lower sum. Okay, so this is when it's an underestimate. Okay, it's lower than the actual sum. Whereas over here, we can see that if we were to find the area of our rectangles, it would be greater than the real area underneath that curve. Well, this is known as an upper sum. Okay, it's above the curve as opposed to below the curve. So this would actually be an overestimate, okay, of our actual area. Now, if the curve is drawn the way we drew it, we can say that a left-hand sum is going to be a lower sum, and a right-hand sum is going to be an upper sum always. But that's only if the curve is drawn in this manner, where it's increasing and concave up. Alright, so consider this next example. So suppose I'm looking to find an estimate for the area underneath this curve between these 2 points using a left-hand sum. Well, here, if I were to start on the left-hand side, I would go up till I hit my curve, and then I would go over and down. Suppose, again, we're looking to do this with just 3 rectangles. So notice here, if I were to do it, alright, this would end up being an upper sum. Right, it would be an overestimate of the actual area under the curve, right? The real area under the curve would be this portion right here that I'm shading. All right, you can see there's some extra area. Okay, last technique is called midpoint sums. So rather than going up on the left side or the right side to determine our rectangle height, sometimes we're told to use midpoint sums. So this is where we're going to look at the midpoint of an interval to determine your rectangle height. So suppose, again, we have a curve here, we're trying to estimate its area, and suppose we want 3 rectangles again. Well, we are going to go from the midpoint, okay, the midpoint of each of these, okay, would be in the middle here. So what we're going to do from the midpoint is we're going to go up until you hit the curve, and then from there you would draw in your rectangle. So again, from the midpoint value, go up till you hit your curve. Notice that depending on, what your curve looks like, some of it might be above it, some of it might be below it. Okay, so here the height of your rectangle is determined by the midpoint value. So that just simply means you go up until you hit the midpoint. Okay, so this height of the rectangle is determined by the midpoint. Okay, and finally, let's look at an example here. Suppose we have this function y equals x squared plus 3. I've sketched it. I've also made a table of values, which you can easily do. Here is the actual question. We're looking to approximate the area underneath this curve from x equals 1 to x equals 5 using two subintervals of equal width, and we want to do it using these three different techniques. So there's really three questions here. The first one, an LRAM, so we're talking about left-hand endpoints. So if we're talking about the left-hand endpoints, recall that what we're looking at here between these two values. Now first of all, if we're looking to have two subintervals, then that means to go from 1 to 5, there's a distance of 4 there, so the width would have to be 2 of our rectangles, okay, if they're going to be equal width. So from there, if we're looking to do it as a left endpoint, we're going to go up at 1 until we hit the curve on the left-hand side. And then from there we go to the right and we make our rectangle. And then from 3 we go up to the curve, make our point, and then go over and down. Now you are not expected to sketch this each time. I do it in the beginning to give you a feel for what it would look like, okay, but it's not necessary. We're looking to just approximate the area. So to find the area here, it's simply the area of these two rectangles added together, okay? So the first one is 2 by, well, to figure out the height of this first one, the height is really f of 1. Okay, so it's really 2 times f of 1 plus the second one has a width of 2 and then a height of f of 3, right? So this height here is determined by when x is 3. So if we look at our table, the y value when x is 1 is 4. The y value when x is 3 is 12. By the way, understand that we can factor out a GCF of 2 here. This is going to be helpful if you have several rectangles, okay? So here we end up with 2 times 16 or 32 for our approximation. And we can see that this is going to be an underestimate of the real area. Okay, next one here, a right-hand sum. So once again, we know our rectangle width is going to be 2 since there's two subintervals and we're going from 1 to 5, so there's a space of 4. So here I'm going to start on the right-hand side, so that would be right in the middle here at 3. I go up to my curve and over back to the left, okay? And then I'm going to go up from 5, right, which is on the right-hand side, over and down, okay? So this time, my rectangle approximation, so we would have, for our area, we would have a width of 2, and then this time I need f of 3, all right, for this first rectangle. And then the second one, the area is 2 by, well, its height is f of 5. So that is 2 times f of 3 is 12, plus 2 times f of 5 is 28. Again, get used to factoring out a GCF of 2. Of course, we don't need it in this simple problem here, but if you have 10 rectangles, you're going to want to factor out a GCF of 2. Alright, so that's going to give us 80, which based on our picture, you can see that's going to be an overestimate. Okay? Alright, give myself a little more room here. So finally, our midpoint sum. So again, we know that our width here is going to be 2 for our two rectangles, but the difference this time is we are going to find the height by using the midpoint. We're not using the left or the right hand side. So the midpoints happen at 2 and 4. So we're going to go up to 2, and then wherever that hits the function, we are going to draw our rectangle in. So you're going in each direction here, right, from where it hits the curve. Okay, you're going to go up to the midpoint, and then you're going to make your rectangle. So here our area would be, for the first one, this has a width of 2, and the height would be f of 2. Alright, plus the second one would be 2 times f of 4. So if we look at our table here, f of 2 is 7, f of 4 is 19, which we know is 2 times 7 plus 19, so that's 2 times 26, so that would be 52 for our area. Okay, and if we look at our graph here, it looks like there is a little bit of space below the curve, a little bit of space above the curve, so we suspect that this would be the best answer. Now in our next video, we will look at finding the actual exact answer using the calculator. Sorry for this long video, but at least it's the only one for this section. Okay, bye-bye.